Hello, good morning or afternoon or evening whenever you are tuning in. Today our topic is the peripheral nervous system. So I'm going to get my notes pulled up here and we'll kind of jump right into it. A shorter unit today to discuss. Okay, so the peripheral nervous system, again, we've kind of done an introduction to the nervous system in general. And so get my pointer going. So you can see that the peripheral nervous system includes things that are lying outside of the central nervous system. So the central nervous system, again, includes the brain and spinal cord, and the peripheral nervous system is going to be kind of pretty much everything else. So things that we're going to focus on in this particular unit include the sensory or afferent neurons. So sensory or afferent neurons are going to receive information and send it back up to the brain. And then also motor or efferent neurons are going to send information from the brain out to an effector. So they can have an effect on organs or muscles and allow us to respond to particular stimuli. That can come in two different forms. So we have the somatic nervous system, which is going to control like our voluntary muscle movements. So let's say, for example, I see a bear. Okay, so I'm going to receive that information from my sensory afferent neurons. They're going to send information to the brain so that it can be processed. And then my motor or efferent neurons are going to send signals to my muscles, the somatic nervous system, that tells me I need to freaking run away or whatever the situation might be. Okay, so that's going to cause us to have some sort of voluntary action. The autonomic system will be discussed in the next unit or in an upcoming unit. We'll be talking in more detail about the sympathetic nervous system and the parasympathetic nervous system. The major difference we see with autonomic in comparison to somatic. Somatic is voluntary and autonomic is basically automatic in nature. So those responses are kind of like out of our control. So again, those are going to automatically happen when we perceive a threat or something along those lines. But more details to come on autonomic system at a later time. Today, let's focus on the peripheral. So starting out with some structures that are found in the peripheral nervous system. Again, we have sensory receptors, and sensory receptors are going to pick up stimuli from the environment. And this can be either internal stimuli or outside or external stimuli, okay? So let me give you an example of either type. So we do have sensory receptors, that are located inside of certain blood vessels, for example, and they're going to monitor changes in pressure. Okay, so those are receptors that are located inside of the body. Maybe we also have some temperature receptors that are located internally that are going to help us to understand what's the temperature of this individual or of your internal organs so that we have a good feel for that. When we think about external receptors, again, we do have temperature receptors located under our skin surface, and that would allow us to understand what is the ambient temperature, like what's going on around me. I also have, like, for example, some different pressure mechanoreceptors located in my skin that would allow me to perceive, like, for example, the strap of this tank top. So again, I can feel that tugging on there because it's activating those sensory receptors that are sensitive to external stimuli. Okay, so again, those sensory receptors can be both internal or receiving information from external sources. Kind of turn, I got that light was kind of like right in my eyes there. Another thing that is included in the peripheral nervous system are nerves or ganglia, and ganglia are bundles of peripheral nerve bodies. So they're nerve cell bodies. So it's like a little coagulation of a bunch of cell bodies sitting together. Nerves are bundles of peripheral axons. Most nerves are mixed, so they will include both sensory and motor neurons. So one thing that's important to note when we think about this, again, if a nerve is a bundle of these axons, keep in mind that each individual axon is only a one-way street. Okay, so an axon can either bring information from somewhere in the body up to the brain, or vice versa. It can take information from the brain and bring it down and deliver it to somewhere else. Okay, so again, important for us to keep in mind that each of those axons are one-way streets. However, a lot of times they're grouped together, so they'll be carried together. And then lastly, motor endings. These are axon terminals that innervate muscles, organs, and glands. So again, these motor endings are going to allow us to stimulate or elicit a response from, the muscles, organs, glands. So it's going to send information about what we want to do. Okay. So when we think about these peripheral sensory receptors, again, we said that the sensory receptors could be either internal or external, and they're going to be classified in two different ways. So number one, they can be free nerve endings, or number two, they can be complete receptor cells. Okay. And receptors, again, can be classified based on their location or the types of stimuli that they can detect. So again, we'll talk about the difference between those here coming up in the next few slides. So let's take a look at how we might classify them based on location. Okay, so we have these exteroreceptors, which, just like what it sounds like, they're going to be sensitive to stimuli that are outside of the body. So this includes touch, pressure, pain, and temperature receptors. So again, we're looking for us to gain information about our surroundings, essentially, with these exteroreceptors. Interoreceptors are also sometimes called visceroreceptors because they are going to receive information about what's going on inside. Okay, so within the visceral organs sometimes. Okay, so we're going to receive information about our internal environment. This can cause us to feel like visceral pain. So for example, if you've got like a side ache or a stomach ache or something along those lines, or if you've ever like breathed really hard when it's super cold out and your lungs kind of like hurt. Okay, well, I'm receiving information about visceral pain in that particular scenario. Nausea, again, if you feel sick. Okay, so again, I'm receiving information from internal or interoreceptors that tells me that I just don't feel good. Okay, hunger and fullness are also going to be senses or sensations that we're going to experience because of these intero or visceroreceptors. Okay. And then the last classification based on location is our proprioceptors. And these are super cool. So proprioceptors are all about understanding body movement, which I think is super interesting because I'm an exercise person. So they're located in muscles, tendons, and joints. So they're going to sense body position and body movement. They can sense, if the muscle gets stretched too far, or is my joint position how I want it to be in order for me to complete this action or this activity, this movement, such as, a sports-specific movement like throwing a ball or something along those lines. So it allows us to understand body position, which can be very, very important in sport, but also, in development as well, as we're starting to learn how to walk and how to control our bodies, right? These proprioceptors are becoming more and more important as we start to learn some of those skills. We can also, as mentioned, classify our receptors based on what type of stimuli they are receiving. So 5 different types. So we have mechanoreceptors, and these are going to respond to like mechanical change. So they're going to be have a response to touch, pressure, stretch, and vibration. So the baroreceptors are one example of those. So baroreceptors are going to receive information about pressure within a vessel. So that's what a baroreceptor is. But again, mechanoreceptor is kind of the more broad term. A baroreceptor is a specific type of mechanoreceptor. But again, this will allow us to have response to touch, So, for example, if I am playing basketball and I'm playing defense and I go to block somebody out, and so I block their shot or try to block their shot, and then I turn around and kind of like put my butt against them basically. I'm relying on my mechanoreceptors in order for me to be able to feel where my opponent is going, right? So pressure against my mechanoreceptors on my posterior side allows me to know where that person is and how I need to react in order to stay in front of them. Okay. Thermoreceptors are going to monitor changes in temperature. As I already mentioned, we have some that are located in the skin surface, but we also have some that are internal as well. So that'll allow us to not only monitor our core temperature, but also monitor what's going on in the periphery as well. And monitor, what's going on with the external environment in regards to temperature. Nociceptors, I think this is super interesting. Nociceptors are pain receptors. And what's interesting about these, in my opinion, is there's not really a standard. There's no way for us to kind of scientifically quantify pain, right? So, you think about maybe different people that or brothers or sisters or things like that, and the difference in how they react to pain, right? So these nociceptors, is it that people that have a high pain tolerance, maybe they don't have many nociceptors, right? So maybe they don't have them, or maybe they just don't perceive them to be as painful as some people that think everything's painful, right? The other thing that I find super intriguing about these nociceptors is our response to pain is highly dependent on experience, right? So if you've been through something painful and you have this sort of standard to compare to, right? Well, I know that this particular incident isn't as bad as whatever this really painful thing was. So I perceive this incident as not super painful, right? I'll give you an example, right? So childbirth, okay? Super painful, really freaking hard and not super enjoyable in the moment, right? So again, if that's the hardest thing that I've ever done, right? And I've done some other pretty hard things. I've done, 12 marathons and 4 Ironman triathlons and multiple other, races and things like that. So as an endurance athlete, I've put myself through quite a bit of pain, but nothing comes close to the kind of the standard, right? So now after having had a child, here's my standard, and running this marathon isn't as hard as what this was. So this doesn't seem as bad, if that makes sense. So when we think about nociceptors, I think that's super interesting that it's highly dependent on how we perceive that to be painful or not painful, depending on past experiences. Also depending on our expectation as well. If you expect something to hurt really bad, right? And then you go into it and you're like, oh, that wasn't so bad, right? Your perception is going to be different than if somebody's like, oh my God, this is going to be the worst thing you've ever experienced. Then your perception is going to be that, yeah, that was really painful or whatever, right? So nociceptors are highly dependent on memory and also dependent on perception or what your expectation is of that particular situation. I recently read this book called The Brave Athlete, and it's all about sports psychology, and super intriguing stuff. But you think about athletes and how having a high pain tolerance is important in order to be successful in many sports, right? So being able to push yourself in your training or being able to push yourself during that competition is very important in order for you to be more successful than someone who's not willing to do those things. And so, it's this concept of, am I drawn to sport, or am I drawn to this particular type of sport because I'm tough, because I have a high pain tolerance, or what? What's the deal? Am I good at this because I naturally have those things? But actually research shows that participation in sports makes you tougher, right? So it's not that you're born with this innate high pain tolerance or anything else, which some people are, but you develop that after putting yourself in painful or strenuous situations, you know, time and time again. You build that pain tolerance, and those nociceptors are affected by that, which I think is super interesting. All right, enough about pain. Okay, photoreceptors. So photoreceptors are going to allow us to detect stimuli from eyes. Okay, so that's what allows us to create images or transmit images into our brain. And then our chemoreceptors are going to sense changes in taste and smell. They're also going to monitor changes in blood glucose levels, so our sugar levels, oxygen, CO2, and hydrogen levels. So they're going to allow us to detect changes in chemicals. Again, we think about those blood glucose, oxygen, CO2, and hydrogen changes. Those are all going to be located in blood vessels. Okay, so we talked a little bit about the different types of receptors. We have free nerve endings. These are most abundant in the skin. So here you can see the nerve endings here. One thing that's interesting about these free nerve endings is their density depending on where under your skin you're at. Okay, so for example, we're much more sensitive like on our lips and on our fingers. So we're going to have a high density of free nerve endings in those locations, and that's going to allow us to really acutely understand where pressure is coming from. And again, super important with our fingers when we think about all the tasks that people can do that require dexterity. Okay, again, places like your back or your calf, for example, we have less density as it relates to these free nerve endings, so we're less sensitive in those particular areas. These are mostly going to respond to pain and temperature. Again, some might respond to mechanical sensations as well, but generally these are going to allow us to respond to pain and temperature. Proprioceptors, again, I kind of gave you a little bit of a glimpse about what these are. They are going to sense changes in body, position, muscle length, joint position, etc. So 3 different types. We have muscle spindles, Golgi tendon organs or GTOs, and joint kinesthetic receptors. Okay. So we're going to take a look at these. So again, if I wanted to have a kind of a definition for proprioceptors, I would say that it is an encapsulated nerve ending that monitors stretch in the locomotor organs. Okay. So again, it's going to monitor stretch and change of position in those muscles, joints, tendons, etc. So let's start with the muscle spindles. Okay. A couple things to note about our muscle spindles. They are located inside or internally within the muscle belly. Okay, so here you can see the muscle spindles here. Okay, and let's see, let me give you a demo of kind of how these work. So the muscle spindles are, like we said, located inside of the muscle. And in order for me to activate them, if I can back you up a little so I can demo this, I have this little board that I want to lift up. Okay, so in order for me to lift up this board, okay, I'm going to place my fingers underneath and pick it up. Okay, it's very light, so that's easy, no problem for me to lift it up. Okay, in order for me to create the tension needed to appropriately lift up this board, I need to activate these muscle spindles. Okay, so what happens? So as these are stretched, which they will be stretched when I place any type of force in my hand. So again, even though this little board is super light, it's still going to activate a little bit of stretch within that muscle. So it's going to activate some stretch in the muscle. Then it's going to send a sensory signal through the spinal cord, and its action is then going to be to activate the muscles or the muscle fibers in that particular muscle. Okay, so again, if we're thinking about lifting this up, the muscles that I'm probably activating are going to be my bicep brachii, for example. So let's go with that one. So again, I stretch out the bicep brachii, I send a signal to the spinal cord, and as a result, I get contraction of that muscle. So again, if I place my hand on my bicep, I can feel the tension. I can feel that that tension is more than if I didn't have anything in my hand, okay? So muscle spindles, when activated, are going to cause the same muscle to contract, okay? So again, how does my muscle know how much contraction is needed to lift up this little board? Well, I have memories, right? I have memories about maybe I've lifted this exact board before in my past, or I've lifted things that are similar to that in the past, okay? So again, that gives me a pretty good estimate of how much work I need to put in order to get this little thing picked up. Okay, so again, we can use those memories to get an idea of how much force we're going to need to generate, you know, based on the weight of that particular object. Also, the amount of stretch activated will play a role in how much force is then going to be produced. So again, I elicited just a little bit of stretch, so therefore I elicit just a little bit of muscle contraction. If I wanted to lift something heavier, this little bucket here with a bunch of mail and stuff in it. So if I wanted to lift this up, again, memory tells me that this is going to be a little heavier than that particular board. And as I try to lift it up, I don't even think I can lift it. There we go. I'm going to get more stretch of those spindles. And so therefore, I'm going to need a stronger contraction in order to overcome that force and create that movement that I want to. That's how muscle spindles are going to work. Golgi tendon organ is kind of like the opposite of that. Okay, so Golgi tendon organ is located in the tendon of each muscle. Okay, and the difference with Golgi tendon is when he's activated, his job is to protect you. Okay, so Golgi tendon, when activated, does the opposite. Okay, so again, imagine that I'm not very strong, and this little bin thingy here has like some weights in it, so it's super heavy. Okay, so as I try to lift it up, okay, I'm going to activate the Golgi tendon organ, and Golgi tendon says, hey, this is too strong, or this is too heavy, you're not strong enough to be able to lift this. So as a result, instead of me being able to lift it up all the way, it's going to stimulate the muscle to relax, which causes me to drop that particular item. Okay, so again, the Golgi tendon organ is set up so that it can protect us from tearing the muscle, basically. If you've ever, you know, lifted weights, for example, and you're doing bench press and you're doing fine and everything's going great, and then you go to get that one extra rep and you just drop the weight, right? That's Golgi tendon organ saying, nope, that's too much. Okay, so Golgi tendon is a protective mechanism. So again, let me review one more time with you what Golgi tendon does. So when he's activated, and he will only be activated if the force is very strong, he's going to send a signal to cause this muscle to relax, which will cause you to drop the weight that you're holding, and it's going to protect the muscle then from being torn or from breaking off of the bone, essentially. So its job is to help you to not get injured. Again, those two kind of work in opposite. When we think about muscle spindles and Golgi tendon, we're activating those muscle spindles all the time in order for us to generate appropriate force to move things. Golgi tendon is only going to be activated when needed, when things are too heavy. Okay. We also have these joint kinesthetic receptors. Let's see. Make sure I have things here. Okay. Okay, so the joint kinesthetic receptors are going to monitor stretch in synovial joints. They're going to send information related to body movement to the cerebellum and cerebrum, which we're going to act as spinal reflexes. Okay, There are 4 types of joint kinesthetic receptors that we could find in a joint capsule. We have the Pacinian corpuscles, Ruffini endings or bulbous corpuscles, free nerve endings, and receptors that are similar to tendon organs. So let's find out more about each of these joint receptors. The lamellar or Pacinian corpuscles are rapid adapting stretch receptors that are ideal for measuring acceleration and rapid joint movement, okay? So again, you think about doing something like generating a lot of force. So maybe I want to jump. So again, as I come down and explode up, I'm going to activate those lamellar corpuscles so that they understand that I'm having a rapid movement occurring. Like as I stretch the muscle, I need to also have that muscle recoil quickly as well. So again, something like jumping. Whew, I'm out of breath from that. Bulbous corpuscles or Ruffini endings are slow adapting receptors. So these are used for measuring positions in non-moving joints and stretch with sustained slow movements. Okay, so when you think about doing like yoga, for example, or holding a stretch, for example, let's say I, I'm so bad at stretching. So let's say I wanted to stretch my hamstring. Okay, so I'm going to reach down for my foot, and let's say I hold it 20 seconds. Okay, now I kind of shake it out, and I'm ready to do it again. The second time I do it, I should be able to reach further now because of the activation of these Ruffini endings. So when I activate these from a sustained stretch position, they become a little more relaxed. So I'm able to again, stretch a little bit further. So again, we use a lot of those principles in yoga or when we do some static stretching. And free nerve endings, again, mainly pain receptors. We already mentioned that some would serve as temperature receptors as well. But the density of these can vary depending on location and depending on the person as well. It can vary from person to person. And then we have these receptors resembling tendon organs. We don't really know what they do. Their function in the joint is unknown. We know they're detecting something within the joint, but that's all we got. But I like that. I think that's kind of cool that we don't know everything. It gives us something to like look forward to. Like somebody's going to figure this out. Maybe one of you is going to be able to figure out what these receptors are actually doing and why we have them. Because there's certainly a reason. We just don't know what it is yet. So I'll leave that to you. Moving on, we're going to take a look at the cranial nerves. So again, we've talked a lot about the receptors that are responding to certain stimuli, so those sensory receptors. And when we look at the cranial nerves, we have 12 pairs of cranial nerves that are going to attach to the kind of that posterior side of the brain and pass through various foramina or holes within the skull. And each of these is going to serve as a different role. Some of them are going to be specifically sensory, some are going to be exclusively motor, and some will be a combination of both. Okay, let's take a look at their functions. Okay, so cranial nerve number 1 is our olfactory nerve, and its function is smell. So again, that's going to be a sensory nerve and allows us to perceive senses of smell. Optic nerve is also a sensory nerve, so it's going to allow us to receive information about vision. Okay, so it allows us to transmit images up to the brain. Oculomotor nerve is a motor nerve, so it's going to allow the eye to move. So it's going to allow us to signal the eye so that we can move our eyes in different ways, different directions. Trochlear nerve is going to work alongside with ocular motor, and it's going to help us with extrinsic eye muscles. So again, that will be a motor nerve as well. Trigeminal, tri means 3, so trigeminal has 3 different things. So the three things the trigeminal nerve does is receive sensory information from the face. So is my face cold? Is something providing pressure against my face, etc., things like that. So sensory to face, motor to the face as well. So again, allowing us to be able to have different expressions and things like that would be one of the functions or a partial function of the trigeminal nerve. And then also motor to the chewing muscles. So again, allows us to chew up our food because it's allowing us to have motor stimulus to those particular muscles. Abducence is going to be motor as well. So the abducens nerve is going to allow us to abduct our eyeballs. So you can't activate both abducens nerves, or I can at least. I don't think the normal person can. Maybe you can. I don't know. You can't abduct both eyes at the same time. So abduction is like, going away from midline. So that would be like one eye going this way, one eye going this way. But we could do one at a time. So that's going to allow me to look in my periphery either direction. Okay. Facial is going to innervate the muscles of the face. So again, that's another one that will allow us to have different expressions and allow us to, change our facial expressions, basically. So again, motor to the face. Let's see, vestibular cochlear is important for hearing and equilibrium. So again, primarily sensory for that one. So we're going to be receiving information from the ears and sending it up to the brain. As it relates to both hearing sound and establishing equilibrium within that inner ear. Glossopharyngeal will be the tongue and pharynx. Okay, so glossopharyngeal is going to send motor information there. Vagus is going to send information to the thorax and abdomen, and the vagus nerve is really important for the peripheral nervous system, which again is one of the units that we'll talk about. But the vagus nerve is going to allow us to basically like activate digestion and things like that. The accessory nerve is going to innervate the trapezius and sternocleidomastoid muscles. So again, it allows us to stimulate those particular muscles and allows them to complete motor actions. And then lastly, hypoglossal. Hypo means below, so this is below the tongue. And this particular nerve is going to innervate the tongue, which would allow us to speak, chew, those types of things with the tongue. In addition to the cranial nerves, we also have spinal nerves. So there's 31 pairs of spinal nerves that are going to attach in various places on the spinal cord. So again, here you can see the spinal cord. Here you can see each of those spinal nerves coming off. And they basically are going to exit, in between each of the vertebrae here. So we have 7 cervical vertebrae and we have 8 cranial nerves. So they're exiting right underneath each of the cervical vertebrae. Thoracic, there are 12. So again, exiting under each of those thoracic vertebrae. Lumbar, there are 5. So again, each one exiting underneath the lumbar vertebrae of that particular location. Sacral nerves, again, there's going to be some small foramen within the sacrum that's going to allow us to have these nerves exit here. So when we look at a cross-section of a spinal cord, again, we said that those nerve bundles would contain both sensory and motor information. So again, they're going to contain both types of axons, but here you can see how they get in and out of the spinal cord. Okay, so here's how they're interacting with that central nervous system. So on the dorsal side, okay, here in the blue, which is the posterior side. So again, if you think about a dorsal fin of a dolphin, it's on the back side. So the dorsal root is going to be on the posterior side of the body. And the dorsal root is going to give us sensory information. So dorsal is sensory. Okay, so our sensory information comes in the back. Again, then that will allow us to interact with the central nervous system. And then the ventral root, which is on the front or the belly's side, is going to send motor information. Okay, so ventral, motor, dorsal, sensory. We also have gray matter, which is going to be internal, and white matter, which is superficial. And those are components of the spinal cord itself. Again, you can see just it's basically the same image that shows us kind of the relationship between dorsal coming in the back, so our sensory coming in the back, and ventral or motor coming out of the front. I think just a couple disorders to mention when we think about the peripheral nervous system. Shingles was one that I selected just because I think this is pretty common. So shingles is a viral infection of sensory neurons that are innervating the skin. It can cause a rash of scaly blisters. It's usually the result of like stress or weakened immune system. So again, you think about like some people get cold sores when they're stressed out, some people get shingles when they're stressed out, or their immune system is down. And treatment for this is usually pain relieving drugs, some sort. Okay, migraine headache is another one that I included just because of how common it is. We think that it's related to sensory innervation of the brain, related to cerebral arteries by the trigeminal nerve. So basically the arteries are going to widen, and this causes irritation to those sensory nerves, and it can cause some super bad headaches. So that's what's going on with those. Again, triggers for people can vary from person to person, and figuring out what those triggers are, I think, is really important to allowing that particular individual to try to prevent, future attacks. But yeah, anyway, that will be it for the peripheral nervous system. Again, please feel free to reach out if you do have questions. Otherwise, I hope you have a wonderful day, and I will see you soon.